Alright, welcome everyone to this final video here on electrochemistry. We're going to talk about the Nernst equation. So first, to get to the Nernst equation, okay, we're going to talk about the cell potential, often also referred to as electromotive force, okay? And the cell potential is related with kind of the maximum amount of work that can be done from an electrochemical reaction, okay? And the key relationship which we'll derive is that the free energy change for that chemical reaction is related with minus VFE. V is going to be the number of electrons that are being transferred, F is Faraday's constant, and E here is your cell potential. Okay. And so, right, how will we get this relationship? So let's start with, again, talking about our extent of our reaction and some change in the reaction, right? Where, again, that change in the chemical reaction is related with the change in free energy with respect to the change in the extent of that reaction, okay? Right, under constant temperature pressure conditions, right, you have this relationship here, dG equals delta RG times d eta, okay? Right, remember we derived a while ago that the maximum amount of work done non-expansion work, right, the max, right, so max non-expansion work, right, is equal to delta G, okay, right, so dG is related with the change in the maximum non-expansion work, okay. And then using the fact that, right, for some chemical reaction where I transfer electrons, right, the number of electrons transferred is related with the stoichiometric coefficient of the electrons transferred times the extent of the reaction, right? So V here is sort of the stoichiometric coefficient of the number of electrons transferred, right? And then the fact that the charge per mole of electrons, which is defined by Faraday's constant, I can use that to get the total charge transferred, right? So the total charge that's transferred is just related with V times Faraday's constant, okay? Which is, and I multiply by a negative here, okay? Because the fact that the charge of electrons is negative, right? And so the electrical work, right, is the amount of charge that's transferred over a potential, right? So electrical work is charged through the movement of charge through a potential. That's how you get electrical work, okay? So that change in electrical work, right, is just going to be minus VF times the change in the extent of the reaction times the cell potential, right? Again, the cell potential is defining the potential of that chemical reaction, okay? And so given that, okay, and then on the previous slide that dG equaled delta RG d eta, right? You know, plugging in then the fact that dG is related with dW, okay, and then plugging this in, we get this relationship here, right? That the free energy change, right, for a chemical reaction is related with minus V, okay, that stoichiometric coefficient, the number of electrons transferred, okay, times Faraday's constant times the cell potential of that reaction. Okay. And so again, what that means, right, for some reaction that's spontaneous, that means, okay, that free energy is changing and going downhill, which means the cell potential has to be positive, right, at equilibrium. The overall cell potential is 0, and the free energy change is 0, right? And, right, if I wanted to go up this, right, then the free energy change is greater than 0, so the cell potential has to be less than 0, okay? Right, and if we recall our talk about equilibrium and free energy, right, we had this equation relate the free energy change of a reaction is related to the standard free energy plus RT ln of Q. So just using the fact that delta G is equal to minus VFE, okay, we can get that the cell potential is related to the standard cell potential, which again is the cell potential at 1 molar concentrations, 1 bar, right, minus RT divided by VF ln of Q. Q is again still your reaction quotient, right? V is Faraday's constant, F again is the number of electrons transferred, and then R and T is your ideal gas constant and temperature. Okay. right? And again, then that standard cell potential is just really the standard free energy change, which again is the free energy change or cell potential when you have 1 mole concentrations, 1 bar pressures. Okay. Right, and so that is the Nernst equation, okay, this relationship between the cell potential at standard states and then at non-standard states, right? Q here is for when we're at non-standard states, okay? Right, Q equals 1 for standard states, right? Because at standard states, the pressures and concentrations, everything is 1, so that ratio of products over reactants has to equal 1, everything's 1, right? Okay, and at 298 Kelvin, this Nernst equation can also be written in terms of the log of Q, right? And has this value of minus 0.059156 volts divided by the number of electrons transferred times the log of Q. Okay. And then finally, relating the cell potential with the equilibrium constant, right? Again, right, we have the Nernst equation, right? At equilibrium, the cell potential is equal to 0, Q equals K. So we have this relationship, okay, which simplifies down to the natural log of K is just related with VFE divided by RT, okay? And so that's, excuse me, how you get the cell potential under non-standard conditions, right? The standard cell potentials are measured experimentally in reference to the standard hydrogen electrode, okay? And then non-standard cell potentials you can get using the Nernst equation, okay, which is related with the reaction quotient, okay, as well as temperatures and number of electrons transferred and Faraday's constant and such.